So do you guys remember what we have been learning so far, or what we have learned in this unit so far? If anybody can do a quick recap or help me recall. And there's a reason why I'm saying so, okay? Because I want you guys to recollect what we have covered so far with respect to function transformation, so that when I start with what we want to do today, you'll be able to connect the dots. So if anybody in the class remembers what we have covered so far, that will be a good jump start. Sana, Nika, Sundara, Disali, Bhavish, anybody? No, I was asking, what are the things that we have covered so far with respect to function transformation? So it's a question to everybody. I'm just trying to recollect what we all know or what all we recall, and then I will take that as a starting point and continue from there. Iksha, anything that you recall?
We learned about reflection.
Okay. Aditya. So we learned about three things. We started with this unit called function transformation, meaning if you have a function represented in a graph, how does it transform? What do we do for making the function, the graph of the function move upward or downward, or how do we make it move laterally? And then we learned about how do we reflect a function. If I have a function which plots a graph, how do we make the function or the graph of the function reflect across x-axis or across the y-axis? Do you guys recall? And then we start talking about scaling a function. Those will be. So just to make sure that everybody is on the same page, I know some of you were missing in last 1 or 2 classes because of spring break, and I'm sure Survi was one of them. So I'm just helping you guys recall that we have started talking about function transformations, where we talked about shifting, meaning moving the graph of a function laterally or vertically. Then we talked about reflection of a graph, a reflection of a function, meaning the graph, how the graph can be reflected across x-axis or across y-axis. And then we start talking about scaling a function, scaling a graph of function. So that is where we will talk about scaling vertically or scaling horizontally. We briefly touched upon scaling vertically in the last class, but we will do both the things together in today's class so that you are able to relate to it. And all the kids who missed the previous few classes, I would strongly recommend, even if I am the most boring teacher, please watch the videos of the classes that you have missed, last 2-3 classes, okay? Because there are a lot of related content that you will be using in what we are going to do today and what we will be doing for next couple of classes before we finish this unit, okay? And those are interesting ones, so I would request you guys to watch the videos of the classes that you have missed so that you are able to catch up on what could be clear versus not clear, and then catch hold of me if something is still bothering you guys. Is that okay? So today we talk about scaling a function horizontally and vertically. So I will try my best to make sure that whatever I teach today, that has no bearing with what we have done in the previous classes, so that if you are coming fresh, you are not totally lost. Is that okay? Is everybody able to hear me okay, or you are just waiting for the speech to get over? Okay. Alright. So we'll talk about scaling a function. So we'll have 2 flavors of it when you are scaling the function vertically, when you are scaling the function horizontally. Okay? So let's take one simple, cute looking function. Okay? Function that doesn't haunt you guys. Let's say I'm talking about a function fx which is equal to x squared. Yeah? Or if you have dealt with this kind of function quite a lot, so let's keep a simple one first. Otherwise, no, it might become a little complicated to comprehend. So I have a function fx equal to x squared. Here also I have a function fx equal to x squared. Same function. When I am talking about scaling this function vertically, I am saying a function gx is created from fx such that it is 2 times of fx or 3 times of fx or 0.5 times of fx. And you guys must be thinking what is going on here. Let's not worry about it. I am saying that when I am scaling the function vertically, I am actually multiplying a function by a constant that helps me scale vertically, and it is still a theory. You have not seen it in reality, so you might choose not to agree to it unless I show it to you guys. Now similarly here, I am saying I am trying to scale a function horizontally so that gx is a horizontally scaled function of fx, and I am saying this is equal to f2 of x or 3 of x or 10 of x, whatever. I am saying when whatever is my input, if I am multiplying the input by certain values, I am scaling it horizontally. When I am multiplying the overall function itself by a constant, I am scaling it vertically, and now you will see why I am saying so. Are you guys okay with whatever I have said so far? Or still not believable at all? Disali, Vasundhara, Nika, Sarah, Bhavish, everybody okay? Okay, there's a starting point. You can still choose not to believe me, okay? Because I'm not given anything to make you guys believe. Ipsa, okay so far? Mm-hmm. Now let's look at this function, f of x equal to x squared. For me, every function is nothing but a contract. When x, so fx, whatever is the fx is output. So I'm trying to plot x and fx. Okay? So when my x value is 0, f of x is 0 square. When x is 1, it is 1, 2, 4, minus 1, 1, minus 2, 4. So when I look at this coordinate plane, I will say this is 1, 2, 3, minus 1, minus 2, minus 3. This is 2, 4, 6, 8. Okay? Let me draw a little bigger coordinate plane so that you guys can see it clearly. So this is my coordinate plane. 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. Here I am saying 2, 4, 6, minus 2, minus 4, minus 6. Now, f of x equal to x squared. I am just trying to plot this. Should be Datta, yeah, everybody with me, right, so far? So should be whatever I am doing, I know you missed a couple of classes, but whatever I am doing it as fresh as possible so that it doesn't have any bearing with what we have done before, okay? And let me know if I am making something complicated. So I am trying to plot f of x, which is equal to x squared. So when x is 0, y is 0, this is my 1 point. When x is 1, y is 1, this is my second point. When x is 2, y is 4, this is my third point. When I go to the negative direction, x is minus 1, y is 1, so again this point. When x is minus 2, y is 4, this point. When I join them, it draws a parabola for us. Yeah, so far. Now, this is f of x. Let's pick this example. F of g of x is another function, which is a transformed function by multiplying our previous function by 2. or yeah, let's pick up 2. So that means if I try plotting it here, a table here, okay, this time I'll have 3 columns: x, f of x, and g of x. And we are looking at this relationship. G of x is 2 times f of x value. Okay. So here, let's put the same points: 0, 1, 2, minus 1, minus 2. It's 0. When x is 0, f of x is 0. When x is 1, f of x is 1. X is 2, f of x is 4. X is minus 1, f of x is 1. X is minus 2, f of x is 4. And again, I just copy pasted this table here. What I'm trying to do is, I'm trying to find out what will be my g of x. We see this value here. Whatever is f of x, this g of x is 2 times of that. So whatever is my f of x value, g of x will be 2 times of that. 0, it will be 2, it will be 8, it will be 2, it will be 8. Yeah? Learn on that. So, and then let me check who all joined before I started my this magical journey. So it's only Ananya who joined in between. Okay. So for Ananya, we are just talking about what do we mean by horizontal scaling and vertical scaling, and how do we relate to it. What I did was, I said, okay, if I have a function f of x equal to x squared, if I multiply this function by a constant, 2, 3, 4, 5, for the sake of simplicity, I took 2 as a constant. I am saying this is going to vertically scale the graph of this function. If you have a function, if you multiply that by a constant, it vertically scales it. We'll see what is happening here. And then we'll look at what is horizontal scaling also. So here, I took this function and I derived another function which is 2 times of the old function, and we are trying to see what is happening here. Okay. So far you have not missed anything. Only thing you'll have to do is watch the video of the class to be able to better relate things. Okay. So now I have started getting a little more demanding with all of you. I have started asking the kids to watch the video of the classes, because that is your best recipe for recollecting what we do in the class. Okay. Otherwise, it's easy to forget. So this is my new transform function where I multiply this function by 2. Okay. Somebody joined. I think there is some Sanvita. Yeah. Sanvita is joined. So Sanvita, you would have probably missed something, but this has some correlation with the last class, so you should be able to recollect. Right now I had a function f of x equal to x squared, and I'm trying to see what happens to this function if I multiply this by a constant 2 or 3 or 4. And that will be my transform function, which is coming by multiplying this function by a constant. Okay. And then we'll relate that with vertical scaling. So here, when x was 0, we had f of x values for 0, 1, 2, 3, 4. This is what we have plotted here. So I will give it a name f of x. Now, let me use another color marker for drawing g of x. When x is 0, g of x is 0. Okay, so this is one point here. When x was 1, g of x was 2. When x was 1, g of x was 2. When x was 2, g of x was 8. Somewhere here. When x was minus 1, g of x was 2. Minus 1, g of x was 2. Again here. When x was minus 2, g of x was 8 again. So same place here. If I join these points here, what did you see? Your graph got squeezed. And that's not the right mathematical definition of it. What you're seeing is your graph's slope increased. Your rise over run increased.
Compressed.
It got compressed. But in mathematical terms, what you're seeing is your rate of increase of y increased. So when you multiplied this function by a constant, it squeezed because your rate of change between 1 and 2 it was changing by, earlier it was changing by 3 units, now it is changing by 6 units. It's growing at 2 times the faster rate. Yeah? If you multiply it by 3, what you will see is it starts growing by a much faster rate. 3 times faster. And that is how this will keep on becoming steeper. Meaning, if you multiply this function by f of x by 25, that means you are making the y move faster for every increase of x. You will see it becoming coming much closer here actually. So it will start becoming more steep, more compressed. So higher the number you multiply with, steeper it becomes, the slope becomes much higher, much faster. Slope becomes much more steep. The rise over run becomes much more higher number. Yeah? Am I making sense now? If you talk about slope of anything, you're talking about slope, rise over run. Meaning for every one change along x, how much is your y changing? Yeah? So basically when you multiplied any function with a constant, your graph started getting compressed. Higher the number, more the compression, steeper this will become. If you multiply by 2000, you might end up seeing this graph becoming like this. On contrary to this, if you multiply this by 0.5, you are flattening it out. So your rate of increase of y gets halved. You multiply by 0.333 or 1 by 3, you will see it becoming even more flat. Multiplied by 0, it becomes horizontal. So what we are seeing is, how do you scale your function vertically is dependent on this coefficient. How you are making it steeper or shallower is dependent on this coefficient that you see here. Does it make sense or not really? Datta is convinced. How about Dishali, Vasundhara, Sana, Bhavish, Aryais, Surbi? Everybody convinced, or I still have an opportunity for doing a better job? How about you, sir? Sure? Okay. So just to summarize this, what we are saying is, if I have a function and I multiply that with a constant or a coefficient greater than 1, then I am making it steeper. I am making the y value change faster. And that's visible here, right? See, f of x equal to x squared versus f of x equal to 5x squared. This f of x is what? Is nothing but your y value, the outcome. Here, this is changing much faster. Here, it's changing slowly. So if it's changing faster, it will make it get compressed, because for every small change of x, your y is changing much rapidly. So this is a perfect example of vertical scaling. How you can scale your graph vertically depends on the coefficient you multiply it with. Multiply it with a higher coefficient, you are making them steeper, making the graph come closer, making the y change much faster for every change of x. If you multiply it with a coefficient less than 1, you are making it shallower, or making the y value change at a much slower pace. Ananya, Sanvita, are you guys convinced? Bhavish, does it make sense better? Okay. So we just saw an example of vertical scaling. Simple takeaway is, multiply your function by a higher value constant and you will make it scale vertically in a positive way or negative way, depending on what you are multiplying it. Now let's come to this one. Now let's come to horizontal scaling. I am purposefully cleaning it up so that I have more space to play with. So let's say I have a function, same function. I will not try dodging you guys by giving different function, misleading, creating any misleading interpretation from this one. I have a function f of x equal to x square, and we saw that if I multiply it with a coefficient 2, 3, 4, 5, I'm making the graph steeper. Okay, I'm making the y change faster for every change of x. Now I'm saying that g of x is a transform function from x such that I'm not looking at x, I'm multiplying or in better terms I will write this as g of x is f of 2 times of x. Does it sound okay? And in between I will keep on taking breaks so that I let you guys digest that information, process it before we try solving it. So we have a function f of x equal to x squared. I'm saying I have a transform function g of x which is equal to f of 2x. So my input changed from x to 2x. Okay. Now let's create a table and we will see what is there in the table. This is not the table from the dining set. It's a table that you guys have seen enough. So what we'll do is we'll define value for x. For different values of x, we'll see what is f of x, what is g of x, and then we'll try plotting them. One honest question to everybody: how annoying my dad jokes get? Are you guys okay dealing with them, or you want me to stop at some point in time? Okay? Okay. So if alone in the class is not able to fight it out, so say okay, we are okay to deal with it. Alright, let's move on. So I have two functions, f of x which is equal to x squared and g of x which is function f2 of x. Okay? So let's try plotting them. When x is 0, so g of x will be what? f2 of x. So meaning whatever is the input is square of that. So g of x will be f2 of x. So meaning wherever I have x, I will replace that with 2x. Square of that, this is 4x squared. Yeah. Now let's see. When x is 0, f of x will be 0 squared, that will be 0. Here, when x is 0, g of x will be 4x squared, so 4 times 0, again this will be 0 only. Now when x is 1, f of x will be 1 squared, that is 1. G of x will be 4 times 1 squared, that will be 4. Okay. When x is 2, f of x will be 2 squared, that will be 4. And this guy will be 4 times 4, 16. When x is minus 1, f of x will be minus 1 squared, that will be 1. G of x will be 4 times minus 1 squared, that will be 4 again. Similarly, when we go for x equal to minus 2, this will be 4, minus 2 squared is 4, and this will become 16 again. Okay? So now, let's create a graph and let me know if you guys are able to see this, if this is dark enough. So this is my graph I'm trying to create. I have 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Here I will use little bigger units. I'll say 4, 8, 12, 16, minus 4, minus 8, minus 12, minus 16. So all that you see here, right, while I am doing this dirty job of plotting it and wasting a lot of time creating this beautiful looking picture, I only want you guys to focus on how I am breaking it down. There is no fancy logic used here. I am just plugging in the value, evaluating the function and putting the values here. That's it. And then how that interprets into a graph is what we are going to see now. So now let's look at f of x. When x is 0, f of x is 0. This is one point. When x is 1, f of x is 1. This is my second point maybe. When x is 2, f of x is 4. I am looking at this point. Okay. When x is minus 1, f of x is again 1 here. X is minus 2, f of x is 4. So I am looking at this point. When I join this, I will join these points. Okay. So let me not extend it. I'll keep it here only. Okay. So that you guys can see what is happening. So this is the graph that I have with f of x. Now I will use another color for drawing g of x. So when x is 0, g of x is 0. So this point is common. When x is 1, g of x is 4. When x is 1, g of x is 4. When x is 2, g of x is 16. When x is minus 1, g of x is 4. When x is minus 2, g of x is 16. Okay, this is one scenario. Now, what I want to do is, I want to change this to x by 2. Okay. So I have another function h of x. I will use another color h of x. I want to show you guys what is changing here. Okay, h of x equal to f of x over 2, and hence this will be, wherever you have x, that will be replaced by x by 2 square, that is x squared by 4. So here in this case what we are doing is, we are changing the input by 2x. We are not multiplying by the coefficient, we are just changing the input here. And let's see what is happening here. Are you guys with me so far, or it's getting a very boring exercise? Sanjita, Survi, Aryahi, Sana, Bhavish, everybody okay, right? Datta? Okay. So this is going to be extension of, so this is my h of x. When x was 0, this is also 0. When x was 1, this is 1 squared by 4, 1 by 4. When x is 2, it became 1. When x is minus 1, it became 1 squared by 4, 1 by 4. When x is minus 2, this again became 1. Now let's plot h of x, and now it will probably give you guys a little more clue. When 0, 0, this point is anyways common. When x is 1, h of x is 1 by 4. When x is 1, h of x is 1 by 4. It's somewhere here. When x is 2, it's 1. When this is minus 1, it's here. When minus 2, it's here. So what is that we are seeing here? You might think that, okay, we are talking about vertical scaling only. We are not scaling it vertically right now. What's happening is, when you change your input by 2 folds, you are making your y grow faster. When you are changing your input by half of what you had before. So here it's not dependent on the coefficient I'm multiplying with, it's dependent on what is the change to the input. So based on how you're changing your input, your slope is changing. So you are changing the horizontal component of your function or the input to the function and see how it is transforming. So this one is called horizontal scaling, meaning when you change the input and then based on that how your function is behaving, you are saying that okay, if I change my input to half, I am making it go shallow. If I am multiplying by a number, if I am multiplying this one, the input by a number, I am making it grow faster. So here, while it might look like both are the same thing, but the way to look at horizontal scaling would be how you are scaling your input to change the output of the function. If you are making it from here, the automatic color one, the black one versus this one where you are multiplying by 2, input you are multiplying by 2 versus you are multiplying by half, how your function is behaving. So this is basically if you are relating it based on the input that you are dealing with, you call it horizontal scaling. If you are multiplying a coefficient and based on that your function's output is changing, that one is called vertical scaling. And this might not give you a very clear picture with respect to the example that you took, but let's say if you deal with a function f of x equal to 2x minus 4, okay, and then you are talking about horizontal scaling g of x value which is f of 2x, and then that will mean wherever you had x, you change that to 2x minus 4. You will see how this function and this function's behavior is changing. Let's look at one example here. I think that would make it much more relatable. Probably this one was not giving you guys that right picture because your x was the same, but if you had a function which was giving you a very clear indication of that, I think that would make it more sense. So let me give you guys a much simpler example. Let's say I had f of x equal to 2x minus 2. And I'm saying I have a function g of x which is f of equal to f of 2x. So if you plug this here, so g of x will be 2 times wherever you had x, you replace that with 2x minus 2. And let's say you had h of x which is f of x by 2. And probably this will give you guys that view of how your graph is changing, how your equation is changing. So wherever you have x, you're replacing that by x by 2. So here this became 4x minus 2 and this became 2 into x by 2, that became x minus 2. So these are two equations that we're looking at. Let's try plotting it on a graph paper. I think that would be a little more relatable. Let's look at it. X, f of x, sorry, g of x and h of x. Okay. So I will, since this is a linear equation, I will just pick 2 or 3 points. When x is 0, when x is minus 2 and when x is 2. And let's see what is the value of f of x. When x is 0, this became 0, this is minus 2. When x is minus 2, this became minus 4 and it's minus 6. When x is 2, it became 4 minus 2, that is 2. G of x was 4x minus 2. So when x is 0, this became minus 2. When x is minus 2, this became minus 8, minus 2 is minus 10. When x is 2, this became 8, minus 2 is 6. H of x is x minus 2. When x is 0, this is minus 2. When x is minus 2, this became minus 4. When x is 2, it became 0. Okay, so are you guys with me with respect to what I've done so far? This was my equation, this was my f of x. It's a linear equation, okay? You draw a straight line for me. I'm saying g of x is f of 2 times x. We are just trying to simulate how does a horizontal scaling look like. So I'm multiplying by 2x. So in place of x, I have input as 2x, and we substituted that in this equation, and we got g of x equal to 4x minus 2. Similarly, h of x, we are trying to simulate what is happening with respect to this function when my input is getting multiplied by half. So this was my new equation, and we got all these tables. So let's try plotting it here. 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and here I will have 2, 4, 6, 8, 10, minus 2, minus 4, minus 6, minus 8, and minus 10. Okay. Here what happened? When x is 0, let's plot f of x first. F of x is 0 minus 2. This was 1 point. Minus 2, minus 6. Minus 2, minus 6. Here. 2 and 2. 2 and 2. This was the line that I was drawing with this one, g of f of x. And I go to g of x. G of x is 0 minus 2. 0 minus 2, this same point. And minus 2 and minus 10. So minus 2 and minus 10. Somewhere here. And then 2 and 2. 2 and 2. 2 and 6 here. And then the h of x is this one. 0 minus 2, same point, this one. Minus 2 and minus 4. So minus 2 and minus 4. This point. 2 and 0. 2 and 0. So what you are seeing right now is you had this was your f of x. When you multiplied by 2, so let me write down the names so that you can relate to it. This is f of x. This one is h of x, and this one is g of x. So if you try relating these, based on your inputs, if your x is scaling horizontally, meaning when you are multiplying by a number, it is making your, this is g of x, it's making your y value go faster based on how you are decreasing your inputs here. This is divided by 2. How your y value is reflecting based on how you are scaling your input. So if you see here, if you look at these 2 points, between this one and this one, what is happening? You are just changing you're just multiplying your input by 2. Based on that, your y value is changing by certain value. And here you're reducing it. Based on that, your y value is changing at a slower pace. So I'm just thinking, why would we even try to relate horizontal scaling and vertical scaling based on inputs? For now, let's go with our understanding that, okay, if I'm multiplying by a coefficient, I'm making the y value change faster. That's vertical scaling. Here, based on my input changing by doubling or by getting multiplied by half or by any other factor, how my y value is changing, that we'll see. But let's look at some problems, okay? I think that will help you guys relate to this concept in a better way than we trying to think through it a little too much. Is that okay? Are we wanting to look at some problems so that it gives us a better ability to look at scaling things? Horizontal, vertical scaling. Only takeaway is this, in two lines. When you are multiplying a function by coefficient, you are making it vertically scaled. You are making your y value change much faster. By changing the input, doubling the input by a certain factor, you are seeing how your y is changing, but you will see that it's only the input part of it, meaning that only the x part is making any impact for this one. Your y-intercept doesn't change. So with the equation that we're looking at, right, your constant was changed. It was y equal to 2x minus 2 or something, right? So your y-intercept did not change. All the three equations that we saw was all passing through this because it did not touch this one. Only this one was contributing to how your y will change based on your inputs. So that is where it relates to horizontal scaling, where based on your input without touching the intercept, you will see that now if you are looking at an equation of a hyperbola like y equal to 2 minus x squared, let's say, it will draw a hyperbola like this. It will draw a hyperbola like this, and when you change the input from x to 2x, meaning you are looking at a function g of x, which is f2 of x, you will see how this whole behavior changes based on the input, and that is where, based on your input, how the horizontal scaling happens here. Okay, so let's look at some problems where we will be able to relate to it a little better. Okay, was it a, I mean, I'm not feeling very convinced, okay, with whatever I was trying to show you guys, but I think when we try solving few problems, that will make a little more sense. Is that okay? Surbi, Ananya, Bhavish, Dishali. Okay, so let's look at some real problems. So that would probably, make this little bit more sense to you all. So let's look at it. Okay. So I'm looking at one problem. Let me pick up which doesn't have much of words. Okay. Here it is -2, -4, -6. This is -2. This is 2, 4, 6, 8. So I have one line that is going from -4 here on the x-axis and touching this at -2 along the y-axis, and I have other line, other graph that is going from here to, let's say, this point, and then going through this. This is f of x and this is g of x. Now let me read the question for you guys. F of x is equal to mod of x plus 2. So we are talking about absolute value function -2. And g is a vertically scaled version of f of x. So when you look at vertically scaled function, this is f of x, g of x is vertically scaled function. This is saying that this is vertically scaled function of f of x. The functions are graphed where f is solid and g is dashed. So this is okay. Don't go by g. This is g, and this is f. What is the equation for g of x? So we have to find out the equation for g of x. So let me read this for you one more time. This is f of x. If you look at it carefully, it's going from minus 4 and at minus x equal to minus 2, it is closer to y equal to minus 2. And then it goes from this point, 0, 0. This is f of x. Now this is g of x. The blue one is g of x. What you are seeing here is this is crossing minus 4 and it meets here at, I think if I give you guys that point, it will make a little more sense. It is meeting at minus 8. This is minus 8. Okay? So this point is minus 8 along the y-axis. So the question is, what is the equation of g of x? And the options we have is, let's brainstorm this. I think that will make a little more sense. G of x equal to 3 times x plus 2 minus 6. Option B is g of x equals 4 times x plus 2 mod of x plus 2 minus 8. Option C is g of x equal to 1 by 3 x plus mod of x plus 2 minus 2 by 3. And option D is g of x equal to 1 by 4 x plus 2 mod of x plus 2 minus 1 by 2. So I think let's look at, so this is f of x, which is going from minus 4 and 0, and this is this point where the tip you see for this one at x equal to minus 2, y is equal to minus 2 here. Now this is g of x, which is saying that this is a vertically scaled version of f of x. When we talk about vertically scaled version, we talk about this getting squeezed, right? So that's what we are seeing here. It says f of x, the black one is mod of x plus 2 minus 1, minus 2. And we have been asked to find out what is the right function for g of x. So how would you guys think about it? I have not taught you guys anything on these lines, but how would you relate to it? What could be a right guess here? Let's do some blind guess here. Let's see what you guys would lean towards, and then we'll try decoding it together. If you have to think about one of the 4 options, which one you would lean on? So this black one is f of x is equal to 1 x plus 2 minus 2, and here are the 4 options you are given for describing g of x. And it is already told that g of x is scaled, vertically scaled version of f of x. So which one you think could be the equation for g of x, and why? Any guesses? Dishali, Vasundhara, Sana, Bhavish? No? So, Datta, any clue? It's kind of getting confusing, right? Okay, so now let's look at it. Whenever you are talking about scaling up or scaling down of a function, or even any function transformation like reflection or shifting, only thing that you look at is what is changing. Here this vertically scaled version of any graph is, it just squeezes the graph, meaning your every change of x results into a quicker change of y. So this is certainly a vertically scaled version, like what we saw before, right? Now, what is the scale? So your approach would be based on what you see in this graph and this graph. What is the relationship between f of x and g of x? Now look at this. Here, between this point and this point, what did change here? Your x value was same, minus 2. It changed from minus 2 to minus 8. So it changed by 4 folds. Yeah? Okay? Your for x equal to minus 2, this changed from minus 2 to minus 4. Okay? Now, I'm sorry, again? 6 points, or it changed by 4 folds. Or here, for this particular point, what you're seeing is g of x is nothing but 4 times of what you have for f of x, isn't it? Yeah? Because for vertical scaling, what we have seen is, if you have a function, you multiply it by a constant, you vertically scale it by that many points. You make it move much faster accordingly, right? So here, whenever you have a function to deal with, when you have a couple of graphs to choose from, you'll always look at, for any particular input of x, what is the relationship between f of x, one function, and the other function. Here, if you look at f of x and g of x, this black one is f of x and this blue one is g of x. Between, for x equal to minus 2, this one is minus 2 and this one is minus 8. So you can say that g of x is 4 times whatever is f of x for this point, correct? Because this is one of the visible points. Everything else will align to it. So whatever it was here, let's say for this point, for x equal to 4, when x was minus 4, both the things are same. Yeah? So if you look at this f of x, when x equal to minus 4, what was happening here? When x was minus 4, so it is minus 4 plus 2. Mod of that will always give you 2, the fixed value. Minus 4 plus 2 is minus 2. Mod of that will knock out the sign. So this becomes 2. 2 minus 2 is 0. That's why you are seeing y value is 0. F of x is 0 here. If it was g of x was 4 times whatever was the x value, if f of x for minus 4 is giving you 0, even if you multiply by 4 or 24, you will still get 0. That's why these two are coinciding at this point. Yeah? Or, I'm not sure if you guys are following me. I am probably not doing a good job today. Let's look at the point that is visible to us. Yeah? Are you guys okay to waste 7 minutes of your precious time with me? Yeah. Let's look at this function, f of x equal to, this is the function given to us, right? F of x equal to x plus 2 in mods minus 2. Let's look at this point. This point is minus 4 comma 0, correct? Now, if I look at the value of f of x, this black line, for this particular point, when x is minus 4, what will be the value of this? It will be minus 4 plus 2 minus 2. Minus 4 plus 2 gives you minus 2 inside the mod. Minus 2. Mod of any number, be it a minus 2 or plus 2, it just gives you the absolute value. So this will become 2 minus 2. That is 0. That's why you are seeing f of minus 4. For x equal to minus 4, your f of x is 0. That's why this black line is crossing this one. Correct? Yeah? Now, let's look at when x is equal to minus 2. What is the value of f of x? When x equal to minus 2, meaning f of minus 2 will be what? Replace x with minus 2. Plus 2. Mod minus 2. Minus 2 plus 2 became 0. Mod of that doesn't make a difference. It is minus 2 only. So your f of x for minus 2 is minus 2. So that's why you are seeing this point making here. Correct? Am I making sense or not really? See, I'm hoping that everybody is clear about what is a mod function, right? If I have, let's say, 5 plus 8 inside the mod versus minus 5 minus 8 inside the mod, both are same. Because this gives me 13 inside the mod, this gives me minus 13 inside the mod. Mod simply means the absolute value. You ignore the sign. That is why this f of minus 4, when we put it here in this one, it got us this value and we see it crossing this point. Similarly, if you want to find out f of 0, meaning when this black graph is crossing this point, is this correct? Is this crossing this point? Meaning when I put x equal to 0, do I get f of x also equal to 0? That is how this point is correct, right? So when you put x equal to 0 here when you are putting 0, f of 0 will be 0 plus 2 in the mod minus 2. 0 plus 2 in the mod is 2 minus 2. This is nothing but absolute value 2 minus 2. That gives you 0. That's why you are seeing this graph is crossing this point. So this is how we draw the mod function. Yeah. So what we saw between this is from this one we found that okay, for x equal to minus 2, my f of x is minus 2. Now we are seeing that for same x equal to minus 2, my g of x, this blue graph, is minus 8. So for the same value of f of minus 2 is minus 2 and g of minus 2 is equal to minus 8. Correct? So the relationship that we are drawing from this is we are saying okay, g of x is nothing but 4 times the value of f of x. Does it make sense? Not really. Not convinced. I'm just trying to read everybody's mind. I think today is not a great day. I've not done a great job. So let me do one thing. In the next class, when we meet on Wednesday, I will not talk about any concept. We'll just muddle the water by solving these 7-8 problems that I've put here. Okay? We'll just solve it from the first thing is let me try understanding this from you guys first. If you hear about something called mod function, what does it mean? Do you guys understand what is a mod function or you don't? No? No exposure? It's okay. I mean, just tell me. I mean, what is your comfort with a mod function? If I say f of x equal to x plus 5 versus f of x equal to mod of x plus 5, what is the difference between these two?
Isn't that the sign for absolute value?
Sorry, bro?
Isn't that the sign?
This is sign for the absolute value. So when you are drawing f of x equal to x plus 5, you will see that it becomes a graph like this. When you are drawing f of x equal to mod of x plus 5, you are talking about this kind of a graph because it looks at the negative values as well as positive values. That is why the mod function is drawn differently. That's what we were seeing, f of x drawing like this and g of x drawing like this kind of thing. So let's talk about the mod function a little bit and then we'll try practicing these problems because you'll see a lot of mod functions coming our way when we're dealing with the function transformations. Bad day? Okay, so let me put this across. If I ask you guys, what did we learn? Anything that you guys can think of if you learned something?
We learned that in reflection.
In today's class?
Yeah. We went to like functions and we learned that.
Little louder than that. What? No, see it one more time. I couldn't.
We did functions.
Okay, we did functions, but we just tried talking about what is vertical scaling and what is horizontal scaling. Just because we have not done enough problems, or we did not do any problem actually. That is why we still have some doubts in our mind, right? So what we'll do is, in the next class, we'll first look at what is a mod function. Because if we look at any function, we just know that okay, you put some value assume some values and correspondingly find out the value of the function and you try plotting it. But as soon as we came across mod functions, we were trying to relate to it, and I felt that no, that is something that I should describe, and then we'll jump onto some problems to be able to better solve it. Okay. Whatever concept I talked about, that might look little complicated to begin with, but I promise when we look at some problems and then try relating to these concepts, it will become much more easier. Is that okay? Sure. Okay. So let's hold it for one more day, and we'll meet again on Wednesday and see if the water gets muddier or gets cleaner. Yeah? Alright? Sana, Bhavish, Sundara, Disali, everybody okay or not okay? I'm not okay. I would certainly want you guys to practice with me before I can become a little more confident than what we are wrapping up with today. Okay? So let's meet on Wednesday, and when we solve few problems, things will get a lot easier. Okay?